Hello, and thank you for tuning in to this session of the MIT Applied Energy Symposium. I would like to give you a high-level overview of our study on modeling renewable energy storage with plasma catalysis. And our ultimate purpose is to assess its feasibility for supporting grid-scale renewables integration. And this could serve as one of the early steps on the path towards a GHG emissions-free energy economy. Now, I'm going to be presenting this on behalf of Maggie, who is primarily responsible for all the analysis you're going to see. So hopefully, during the ensuing discussions, you can direct all the tough questions to her, and then let me handle only the extremely easy ones. I think that sounds like a fair deal to me. All right, so here's what I'm going to cover. I'll first present some background on the plasma catalysis for energy conversion and storage. I'm going to discuss our modeling strategy, present some results, and then summarize the study outcomes. While I'm going to be unable to go into any meaningful detail with the modeling design, we're going to make the code available publicly, so you're welcome to let us know if you're interested. So one of the primary challenges of power production from renewable sources, and here I'm talking about something like wind or solar, is that it is highly intermittent. So it's variable, it fluctuates, and then sometimes it's hard to even predict this pattern. The second problem, which is very much related to the first one, is that very often, the renewable power supply does not match the demand profile. So there's a kind of a temporal mismatch between supply and demand. So the primary hypothesis behind this study on renewable energy storage with plasma catalysis is that it can regulate renewable energy availability and thereby can resolve this temporal mismatch. And then both of these will end up improving the overall grid resiliency, especially in the face of increasing levels of renewables integration in the grid. So let's talk a little bit about the underlying technology. So first, plasma. Plasma comprises, a rich medium of highly ionized gases and also energized high-energy electrons, which are created from the interaction between the gas stream and an external electromagnetic field. Some of the most common configurations are the dielectric bed, gliding arc, and microwave plasmas. In that order, so the dielectric bed is usually the least energy efficient, and the microwave are the most energy efficient. However, dielectric bed has a better conversion efficiency than gliding arc. Microwave tends to perform better generally, but then they do require some vacuum conditions to meet those kind of levels of performance. So that is one of the big limitations there. Now, the reason that we are interested in plasma is that the conversion reactions involved in power to gas conversion are usually thermodynamically inhibited at ordinary conditions, but then they can proceed very often in plasma environment. And this is because the highly energetic plasma mixture can transfer this energy to the localized reacting species, thereby creating a kind of a local equilibrium state that facilitates the conversion reaction. But what's more, it's also flexible because the electricity input that enables the plasma generation can be turned on and off in response to electricity availability. And this is a feature that makes it amenable for integration with variable renewable sources. But then why worry? I guess the main worry is that the current state of the art of these plasma technologies has obvious limitations, as you can see in the chart I have on the right. And then the question we're trying to ask is, within this limit, how well can plasma catalyzed power-to-gas technology provide flexible storage to support renewables integration? So let's say we have wind or solar farms generating renewable electricity to the grid to meet some specified electricity demand. So when there is more generation than needed, we can redirect the excess electricity to a power-to-gas conversion reactor where it provides the energy to generate plasma, which can help transform some primary feedstock into a higher value energy vector, like hydrogen or syngas. Now, this product gas can be reused to produce supplemental electricity when there is a deficit in the power supply from the renewable source. Alternatively, you can also use it as a precursor feedstock to a wide range of chemical manufacturing processes. I think this capability and this level of flexibility is one of the reasons that makes this technology attractive and promising. So, in order to assess the performance of the plasma catalyzed energy conversion for this application, so we design an analysis problem to determine if it's an effective flexible storage option, whether it can provide sufficient capacity, and of course, related and integrated to these two earlier points, whether it is efficient. And here I represent the experiment we set up in order to address these questions. So first we have a renewable energy source, in this case a wind farm, and then we have a feedstock, which for this particular application is biogas, a mixture of CO2, methane, and a little bit of oxygen. Now we supply the electricity to the plasma reactor and then use that to convert the feedstock into syngas, which we now store in some gas storage medium, in this case a pressurized tank. Now, when there is a deficit in electricity from the wind farm, we now supply the syngas to gas turbine to generate power, to make up for this deficit. So this is more like the setup of the experiment. Now, the plasma reactor we're using, the reference data is based on the gliding arc generation technology. These typically have low CO2 conversion and relatively high energy efficiency, and I've included a reference from where we source the data. So to model this system, we use Modelica. It's an open source object-oriented programming language that is really ideal, for complex and dynamic multiphysics modeling of systems. It has a very, very useful feature, which supports functional markup interface. So this really makes it very easy to, share or reuse code. And also its object-oriented structure, and acoustic modeling, sort of ensures physical integrity between interfaces, and also frees up the modeler to really focus on just designing the system, not on how to solve the underlying mathematics. So the figure on the left kind of illustrates the class structure for our model. You can see that you do have the higher level classes extending or inheriting the lower level ones, and then this really facilitates decoupling of the individual components of the model. And it theoretically can support an infinite level of number of layers, but this is sort of the size that we use here. So what we did was that for each of those components, we built either a representative physics-based model or a surrogate model. So for example, for the case of the reactor, we do not really use a detailed reactor model because we don't represent the plasma kinetics. But instead, we use a surrogate model that does capture the dynamics, based on the data experimental report for the gliding arc plasma. But of course, it does handle also the thermodynamics and the energy balance for that reactor. I won't go into this in detail, but the idea is just to highlight that, with this tool, you can also build physical models, or you could use transfer functions to represent actual operational dynamics. So, like I explained, so we go ahead and we build the different models for different components. So here I'm showing just a kind of a representation of the heat exchanger model and also the compressor model. So we have sub-models like this. Like I mentioned earlier, they're going to be available, so I won't really bother going into details to explain them. But at the end of the day, after building individual components and testing them out separately, we now combine them and integrate them into the single unified dynamic simulation. Okay, so let's talk about the results from this study. So the first has to do with flexibility. So can we provide flexible capacity? And you can see from the power supply, the curve of the power supply to the grid, that this plasma catalyzed hybrid plant is able to demonstrate kind of efficient dynamic response to the variability of the renewable source. So it's able to really match the demand for additional energy from the grid. However, from the chart on the left, you also see that in this time period, it does not have sufficient capacity to meet the deficit. So in a sense, we needed to borrow additional syngas from somewhere in order to make up for the capacity deficit. You're going to see that this really has to do with the efficiency of the system, and of course also the particular characteristics of the wind power supply profile for the month that we considered. But in any case, it's a very important consideration that really goes a long way in speaking to the viability of this storage option. Now, still on this topic of flexibility, there is also a cost that goes along with dynamic operation. There's a reason why chemical plants like to operate at steady state, because dynamic operation creates these transients that can result in less than optimal yields. So for example, if you look at the chart on the top right, follow the green for CO2, you see that the CO2 conversion does in the ramping stage, it goes from it does change gradually up to the optimal steady state value and then stays there for the rest of the period. What the chart on the bottom right shows is that for this particular analysis, the plant spends about 50% of the time in this ramping mode. This means that the conversion efficiency takes a further hit. So if you're going to take anything from this slide, it's that dynamics matters. And then because you're ending up with a reactor exhaust that has about 75% of its expected energy density, assuming that steady state operation over the entire period. Now, what about efficiency? So here I'm showing kind of a series of charts that takes you through each component in the model, starting from the system inlet all the way through the plasma reactor to the gas storage, the power island. And then you see that for each step there is some efficiency penalty. So through the plasma reactor, it takes about 15% efficiency penalty hit. Single storage for the compression, maybe around 10%. And the redispatch, significant amount. And you end up with a round trip efficiency of about 45, less than 50%. Now, to put this in perspective, you can compare it with the efficiencies for different storage technologies. Imagine if you stop with just storage, you find that the power to gas plasma catalyzed reactor does do pretty well. It's 85%, somewhere in between the battery and the pump hydro storage. But then when you consider the round trip efficiency, there is a much more significant penalty, and we have a much lower overall efficiency. So this goes to highlight the fact that the biggest impact you can make in improving the performance of this technology really has to do with an enabling technology, which is the technology you use to redispatch the power. So for example, replacing the combined cycle plant with maybe a solid oxide fuel cell could improve the round trip efficiency. But of course, this is still a technology that's under development and not ready for use at the moment. Anyway, so let's wrap up this presentation. I guess one major takeaway is that plasma catalyzed energy conversion can provide flexible storage However, its effectiveness is limited by storage and redispatch penalties, which means that we really need to investigate other technologies that can improve these efficiencies. Now, other issues worth addressing include the geometric footprint of the storage system, because we're storing gas, and also the scale-up strategy for the reactor. We have to figure out what should be the optimal dimensions of individual reactors that make up for the reactor unit. So with that, I would like to thank you very much for listening. We look forward to your thoughts, comments, and questions in the discussion forum. Thank you very much.